Alright, now we're on to the very last IA of this school year, and the units that we're covering are circuits, mechanical waves, and E&M waves. There will be very little circuits, only 2 questions, but the majority of the test will be on mechanical waves and E&M waves. Alright, so number 1. What is the frequency of a light wave with a wavelength of 6.0 times 10 to the negative 7 meters traveling through space? Okay, so we're talking about light. This is something that you guys should remember, but in case you forget, it will be on your reference table. It is the speed of light in a vacuum. 3 times 10 to the 8th meters per second. We typically denote it with the variable c to denote that it's the speed of light in a vacuum, not the v velocity that we're all used to. And we're figuring out the frequency of a light wave. So this is our equation. V is equal to f lambda. F is our frequency, lambda is our wavelength, and let's plug it in. Should get a choice D. Alright, number 2. Wavelength of X-rays with a frequency of that, traveling in a vacuum. Okay, same thing. This time we're looking for lambda. We should get a choice C. As a note, our waves are typically going to have very short wavelengths, so we're going to expect negative exponents, unless we're dealing with the longer waves, like radio waves. And on the other hand, frequency is going to have a very high number right there, high power of 10. If we look at number 1, 10 to the 14th. If we look at number 2, 10 to the negative 10. So for our wavelengths, we expect very small numbers. Frequency, very high numbers. Okay, number 3. Hey guys, I'm using all 3 of my favorite colors. Wink, wink, nudge, nudge. Please remember that. No, you don't have to. The time required for light to travel a distance of 1.5 times 10 to the 11th meters. As a note, I made a mistake here. None of these answers are correct. I copied the wrong answers, guys. Alright. We're looking for time. This is our only relevant equation here. Speed of light still stays the same. Our distance is 1.5 times 10 to the 11th meters over time. When you're looking for time, you gotta make sure you put the distance on top. So this is how it should be. You're multiplying time on both sides, and then you divide by 3 times 10 to the 8th to get time by itself. Alright, and you should get 500 seconds. Four is very similar to some previous questions, same spiel. Same equation, same speed. You should get 3 times 10 to the negative 2 meters. Alright. 5. Compared to the speed of microwaves in a vacuum, the speed of X-rays in a vacuum is... This is a trick question, guys. They're the same. But why? Alright. So microwaves and X-rays, they're both part of the E&M spectrum. Therefore, their speed is still the same speed. They're all types of light waves, all types of electromagnetic spectrum waves. Therefore, their speed is 3 times 10 to the 8th meters per second in a vacuum. Doesn't matter what type of wave it is, they all share the same speed. Which wave characteristic is the same for all types of electromagnetic radiation traveling in a vacuum? Same thing. Speed. They're all types of waves, all same speeds. But let's go through each of these choices though. Wavelength. Each of them has its own wavelength, each of them have its own frequency. Each wave has once again has its own characteristic wavelength and frequency. And period is related to frequency, so if they have different frequencies, they're going to have different periods. There we go. Okay, compared to the speed of light in a material medium, the speed of light in a vacuum is, let's analyze this, vacuum. Vacuum is simply space, nothingness, just an empty void. Very sad, empty void. Material medium. That means we have particles. It has particles. Regardless of what type of particles, there's something there. Not empty. So let's think about that. Do you think you'll move faster in something that's empty or something that's full of stuff? We're obviously going to move faster in the vacuum. Faster in vacuum. And as we learned in class, the speed of light changes when we go from different materials. The speed of light in a vacuum is actually the fastest. Light travels fastest in vacuum. Changes speeds in different materials. Alright, so the speed of light in a vacuum, so we're talking about the vacuum, it's going to be greater. Alright, number 8. As the frequency of an electromagnetic wave increases, its speed in a vacuum will. Alright. So what do we know about this now? What is the speed of light in a vacuum? It's this number. When does the speed ever change? When we go into different mediums. So it stays the same. Speed in vacuum never changes. Alright. Number 9. A microwave and an X-ray are traveling in a vacuum. Compared to the wavelength and period of the microwave, the X-ray has a wavelength that is what? Alright. If you check your chart, you should look at the chart. Check your E&M spectrum chart. It's in the reference table. You will see that the X-ray is on the left side of the spectrum. That means high frequency, short wavelength. X-rays, high F, low wavelength. Okay, so the X-ray is going to have shorter wavelength. And if it has a high frequency, what about its period? It's going to have a short period. Okay? If you think about this, F is equal to 1 over T. They have an inverse relationship. If F goes up, T goes down. So if it has a high F, it's going to have a low period. Short wavelength, short period. All right, number 10. Gotta make this quick. I got Game of Thrones coming up, guys. Electromagnetic radiation having a wavelength of 1.3 times 10 to the negative 7 meters would be classified as what? All right, check your chart again, guys. So here you're gonna look at the top portion of the chart where it's wavelength. We're gonna go to 10 to the negative 7 meters. 1.3 is a little over that, but we're still within the ultraviolet range. And looky here, we're using a color that's close to violet. Check your chart. You cannot answer this question without that chart. All right, number 11. The color of visible light is determined by its what? So what do we know? Different colors. Roy G. Biv. Have different wavelengths and frequencies. So part of it is mostly determined by its frequency, because we don't see wavelength. Period is related to frequency, but primarily it's wavelength and frequency. All right, number 12. A ray of light strikes a plane mirror at an angle of incidence equal to 34 degrees. The angle between them is, so let's say we have this, our plane mirror and our normal line. We have a ray of light striking this, 34 degrees. Reflection. That means it bounces off at the same angle. Okay? So the angle between these two, 34 plus 34, we double it, we get 68 degrees, guys. And I'll be right back because Game of Thrones is on. All right, number 13. We have a light ray incident upon a plane mirror. So this is our mirror. Don't forget, you always gotta draw that normal line. And if we have an incident ray, we're gonna have a reflected ray equal and opposite. What do we know about these two angles? They're always equal to each other in reflection. Alright, so if this goes up, this shall also go up. Yes, choice B. Number 14. Pencil appears to be bent at a point where it enters the water in a beaker. This phenomenon is called, guys, you should know this, refraction. So let's draw that little beaker. If we have here a pencil, appears to be bent. Refraction. Okay, 15. The diagram below shows a light ray in air incident on a crown glass block. As the light ray enters the crown glass block, it will what? Okay. from air to crown glass. The N value of air is equal to 1.00, while the N of crown glass is 1.52, I believe. Alright, and what have I taught you guys? If N goes up, the speed of light in a different medium will go down. So here it's going to slow down because of C and D. Now we're looking at A and B. What else did I tell you guys? I told you guys blah, blah, and LBT. In this case, we're looking at LBT. Little to big and little to big. So it's going to go toward. Alright. Slow down and bend toward the normal. It's going to bend closer here. Toward the normal, guys. Okay. Okay, number 16. What occurs when light passes from water into flint glass? Alright. Water is going to equal 1.33, and the N of flint glass is 1.66. At this point, I've had it memorized. What a sad, sad life. So here, N is going up, speed is going down. What else? Wavelength also goes down. And what about frequency? Remains the same. Okay? So its speed decreases, its wavelength goes down, and frequency remains the same. Choice A.